A comet 5 kilometers wide and traveling over 100,000 kilometers an hour has just been discovered. Scientists have calculated that it's on a collision course with the Earth and will impact within the next 24 hours. Humanity can only cry and head for shelters with the realization that civilization is at an end. The comet hits the Earth with the impact of a 100 million megaton explosion. The entire planet is engulfed in flames as 5 billion people are immediately vaporized or poisoned by toxic fumes. Those who do survive suffer through a decade-long nuclear winter and ultimately starve or freeze to death. Only the cockroaches and rats are left to inherit the devastated wasteland of a dying planet. This is not wild science fiction or fantasy. Instead, it is a prophetic view of our ultimate destiny. In fact, this comet impact scenario was a very common event out of the Earth's past. There is no question that a future impact with even a medium-sized asteroid or comet could easily extinguish all humanity on this planet. The only question is when. As inhabitants of Earth, we should not only be concerned about the next comet or asteroid impact, but also about what could be done to avoid or at least minimize the destruction in the event it does happen. In addition, brand new research on these cosmic travelers clearly indicate how they may have been responsible for giving us our oceans and depositing the very seeds of life from which we came. Both comets and asteroids might well have played the greatest and most significant role in Earth's history by both giving life and taking it away time and time again. Both comets and asteroids are essentially the leftover debris from the birth of our solar system, when the sun and planets formed over 4.5 billion years ago from a ball of dust remaining after the explosion of a star. Asteroids are irregularly shaped objects, ranging in size from a few meters to over 1,000 kilometers in diameter, and are generally found in what's known as the asteroid belt between Mars and Jupiter. Over 3,000 of them have been named and cataloged, and astronomers believe that there are 100,000 or more that can be seen.
There's another population whose existence was only discovered about 65 years ago, and that's the Earth-crossing asteroid population. The population of Earth-crossing asteroids constitute a giant swarm of objects, which may be as numerous almost as the main asteroid belt. It's just that we haven't discovered very many of them. It's just an enormous population. You have tens of millions, maybe 100 million, which are larger than a small house. It's just a huge swarm. Every once in a very long while, they can collide with our planet. The asteroid collision hazard is real.
As a result of the overlapping orbits of these Earth-crossing asteroids, tens of thousands of collisions have occurred throughout Earth's history. A future major impact can occur at any time. In contrast, comets are made of ice and rock. Their spectacular tails occur when the solar wind evaporates bits of ice and dust and blows these particles back for millions of miles. Scientists believe there are trillions of comets beyond the furthest planet in a formation known as the Oort cloud, and that comets are periodically dislodged from their distant orbits and hurled toward the sun. Many comets make only one pass through the inner solar system during their lifetimes. Because of the highly irregular orbits of most comets and asteroids, the majority of them go unnoticed until they're practically on top of us. Take, for example, Japanese amateur astronomer Yuji Hayakotake, who in January 1996, using only binoculars, discovered a comet large enough to destroy all life on Earth only a few weeks before its closest approach. Named after its discoverer, Comet Hayakotake was well over 5 kilometers in diameter when it passed to within only 15 million kilometers from Earth, a near miss in astronomical terms.
I think the public had to have witnessed the close encounter of comet Hyakutake, so relatively close to the Earth, and this had been found by a Japanese amateur with binoculars only 3 or 4 weeks before. I think this has got to remind us all that these planetary bodies can't appear without any warning, and we have to, based upon that sort of thought, remember that we are very vulnerable.
Contrary to popular belief, a civilization-ending impact could come practically without warning. Because impacts with asteroids and comets are so rare, tracking and emergency preparedness funding is scarce or even non-existent, and there is little or no public awareness of such impending dangers.
In general, the astronomers look at maybe 10 or 15% of the sky. So most things coming in would be missed. If you ask the question at today's level of effort, what warning we would be likely to have of the next impact, the most likely warning is 0. The first you would know about it is when you felt the ground shake and saw the plume of hot rock vapor coming up over the horizon.
What few people realize is that if there was to be an impact of even a medium-sized comet or asteroid with Earth, the devastating environmental consequences would certainly spell the end of humanity and the extinction of most, if not all, plant and animal species. As a comet or asteroid enters the Earth's atmosphere, it would heat up to incredible temperatures and either explode above ground or slam into the Earth, dredging up billions of tons of soil and rock.
The first is that an object will inject dust into the atmosphere, which the winds carry all over the Earth. And that dust blocks part, or in some cases nearly all, of the incoming sunlight.
Comets, and to a lesser extent asteroids, can also contain huge amounts of organic molecules embedded in ice. An impact delivery of these exotic chemicals would further add to the destructive effects on the ecosystem.
For example, comet Hyakutake, and indeed most other comets, contain about 0.1%. Ice is in the form of hydrogen cyanide. Hydrogen cyanide, for those of you who may not know it, is what we use in some places to execute criminals. This is a highly poisonous gas and would definitely be unpleasant to have, say, 1 billion tons of this delivered to the Earth's surface intact.
The cloud of dust and poison gas from an impact event would plunge the Earth into a period of complete darkness lasting several months or even years. Since sunlight is necessary for plant growth, any long-term loss of sunlight would bring about the collapse of the food chain.
The second environmental effect that seems to be important for large impacts is that the impactor blasts a plume of material very high, thousands of miles above the Earth, which falls back over the whole planet. And as it falls and re-enters the Earth's atmosphere, it flashes into incandescence, producing a tremendous short-lived thermal pulse and igniting the forests and grasslands.
All of the ash and smoke produced from these worldwide fires would also contribute to the global darkness and nuclear winter, resulting in a lengthened cold spell and increased damage to the environment. The planet would end up being nothing more than a devastated wasteland, and a residual semi-permanent upheaval in climate would kill off most of the life forms surviving the poison gases, flash fire pulse, and nuclear winter.
So I think the answer is that we should avoid these impacts at all costs. They're harmful in many different ways.
The asteroid and comet threat became visible only recently after studies by dedicated astronomers. Scientists immediately appealed to Congress and NASA for funding to speed up a program of detection and tracking of these potential disasters.
They are the only natural hazard that we have the potential of doing something about. There's no one that can imagine a way that you could stop an earthquake from happening or tame a hurricane or plug up a volcano. But if we had adequate warning of a comet or an asteroid headed toward the Earth, then we do have the technology to deflect it, to change its orbit so it would miss.
The U.S. Congress gave NASA the go-ahead to study the potential dangers posed by the Earth-crossing asteroids. However, to date, funding has been approved only sparingly. One of the few tracking stations set up so far is at an Air Force base on one of the small islands of Hawaii. This remote tracking station, far away from interfering city lights and smog, is ideally situated for the tracking of comets and asteroids.
The thrust of our activities now has to do with NEAT, Near-Earth Asteroid Tracking, which is a NASA JPL, Jet Propulsion Laboratory, project in collaboration with the Air Force facility in Maui. We have placed or installed our electronic camera system on their 1-meter telescope. And in this collaboration, our main objective is to search and discover near-Earth asteroids and comets.
So you would need to imagine carrying out a comprehensive survey, looking for any of these objects, finding them, and projecting their orbits forward in time, and thereby locating the one dangerous one out of the many others that do not pose any hazard, locating it in time that you could develop a defense system, send a spacecraft out, examine it, and ultimately deflect its orbit.
The option that appears to be within our technological grasp at the moment is also the most controversial and least desirable. It is suggested that a number of spacecraft carrying small nuclear bombs could be targeted to intercept the object. The spacecraft would carefully deliver these devices to the surface or the path of the asteroid or comet and detonate the bombs. Using the force of the explosions to change the velocity and trajectory, even a small fraction of 1% would be enough to ensure that the object would miss Earth, assuming that the procedure is done several months or years in advance. However, this plan has several serious problems and dangers. First of all, if a problem develops with the launch of the rocket, the nuclear weapons could detonate on the launch pad. In addition, once the nuclear weapon has been launched, if the rocket booster fails while in orbit, it could re-enter, break up, and scatter nuclear material over a widespread and populated area. Furthermore, even if the device gets out to the target, should the bombs be set wrong, the object may splinter into many medium-sized pieces. This would result in multiple impacts occurring randomly over the surface of the Earth, which may well make matters even worse. A wide variety of non-nuclear ideas are also on the table. One plan uses solar energy deflectors carried by satellites to focus sunlight on the object. The heated spot would cause the object to react like a rocket, changing its course as the surface material vaporizes. Avoiding impact with a comet or asteroid in the future may be difficult or impossible. Earth and the other planets in our solar system are essentially huge targets in a cosmic shooting gallery, and have been so since the beginning of the solar system. A look at the Moon shows just how many impacts both the Earth and Moon endured throughout history. We can appreciate the tremendous extent of cosmic bombardment by looking at the results of such impacts on some of our neighboring planets. In mid-July 1994, telescopes around the world were focused on the planet Jupiter. People worldwide were witness to the most spectacular astronomical event in recorded history. A string of over 20 ice and rock fragments from an ancient comet smashed into the planet Jupiter. Astronomer Carolyn Shoemaker, geologist Gene Shoemaker, and amateur astronomer David Levy discovered the comet in March 1993 during a survey of the sky at the Mount Palomar Observatory. At the time, no one was sure what effect these impacts were going to have on Jupiter.
At one point some months ago, we thought the largest might be about 3, maybe even 4 kilometers across. If they were that large, then altogether these comets would deliver about 100 million megatons of energy.
Shortly after the comet's discovery, astronomers at the Massachusetts Institute of Technology ran numerous computer simulations on the possible impact locations and effects on the planet. The comet fragments were to impact Jupiter over a period of 6 days, although these impacts would occur out of view from the Earth. Fortunately, the Galileo spacecraft en route to Jupiter was in a perfect position to view these impacts head-on. The spacecraft was able to transmit incredible images and data of the impacts. As a result, we learned that each of these explosions affected an area larger than the entire Earth. Had any one of the impacts occurred here, all life forms would have unquestionably been extinguished.
Thank goodness we had grandstand seats for this. Otherwise, these Earth-sized impacts would have completely swallowed up our planet. We would not be here talking about it.
In 1986, the Voyager 2 spacecraft made a very close flyby of the seventh planet Uranus, a huge gas planet with rings and dozens of moons. This probe confirmed earlier reports that the planet was somehow knocked over on its side, with the south pole facing the sun. It has been suggested that Uranus suffered a major impact with a huge object of even greater force than the Shoemaker-Levy comet had on Jupiter. The impact with Uranus knocked the planet on its side, creating the rings and moons from the debris of the impact. The tremendous amount of energy of an impact required to knock a huge planet like Uranus on its side would most certainly have reduced the Earth to rubble had the impact occurred here. Closer to home, rocks brought back from the moon's surface by the Apollo astronauts indicate that the Earth was the subject of a major impact in its distant past.
Very early in the Earth's history, we are fairly sure it was struck by an object about the size of the planet Mars, which ruptured the planet, ejected a great deal of material into orbit around the Earth, and it is that ejected material from a giant impact that ultimately formed the moon.
By just looking at all of the craters on the moon's surface, it's clear that our neighboring satellite has endured thousands upon thousands of impacts. Since the Earth has over 20 times the moon's surface area, there simply must have been tens of thousands of impacts on the Earth as well. Perhaps the most famous and extensively documented major impact event here on Earth occurred about 65 million years ago. Scientists believe that either an asteroid or comet measuring at least 10 kilometers in diameter hit the Yucatan Peninsula, leaving a crater 200 kilometers across, which is now buried under new sediments. This huge crater fractured the limestone rock that underlies the region for a distance of several hundred kilometers. Although there is little question as to the occurrence of this impact event, paleontologists still hotly debate whether or not this impact caused the extinction of the dinosaurs. However, geological evidence indicates clearly that well over 75% of all plant and animal species on Earth were extinguished almost immediately after this impact.
Sometimes people talk about the debate about how long it took for the dinosaurs to become extinct. Was it thousands of years or millions of years? I think probably the dinosaurs went extinct in between 30 and 40 minutes. About the length of time it took for this global heat pulse to roast any creatures that were above the ground and were exposed to this flash of heat.
As if the global thermal heat pulse and long-term winter weren't bad enough to disrupt the ecological balance of the planet, scientists now believe that this impact had yet another detrimental effect.
Various people have demonstrated that the basement rock at the Yucatan is indeed limestone, but it's a sulfur-rich limestone. And when this sulfur was dredged up and blanketed the globe, it formed sulfuric acid in the Earth's atmosphere, and this caused a sulfuric acid rain, which was quite harmful to the life forms, plant and animal on Earth.
It is most ironic that the carnage and devastation caused by this impact event paved the way for other animal and plant species to evolve into many of the life forms we know today, including our own ancestors. Virtually all of the other traces of impacts endured by the Earth are erased almost as quickly as they appear, such that all impacts, except the most recent, go unnoticed.
Perhaps the best known example is Meteor Crater in Arizona. That was made by an impact of an iron object about 100 feet across. And it exploded with an energy that we can estimate from the crater itself as about 15 megatons, about the size of the largest nuclear bombs. It left a scar. It's 50,000 years old, and there are half dozen other craters on the Earth of similar age that are also easily seen.
One of the most recent impact events on Earth occurred in a very remote and uninhabited part of Tunguska, Siberia in June 1908. A relatively small asteroid the size of a 25-story building, made up of a loose conglomeration of small rocks, became so hot from the friction as it entered the Earth's atmosphere that the asteroid itself came apart and exploded in a massive ball of fire before it even hit the ground. The explosion flattened and set fire to thousands of square miles of forests. It wasn't until the late 1950s that reporters were allowed into the area, and from their pictures, scientists were finally able to piece together what had happened. If the same type of object would hit New York or other highly populated areas, there would most certainly be deaths and casualties in the tens of millions. However, not all asteroids and comets should be viewed as dangerous or harmful to the health of the human species. Scientists now believe that we owe our very existence to these heavenly bodies. Furthermore, they quite possibly could hold extractable resources exceeding our wildest dreams.
I think we have to keep in mind that these objects are interesting from very positive points of view. We can be exploring these most accessible, very interesting, fascinating new worlds now, whereas the chances of having to worry about a collision during our lifetimes is extremely small. It's not something we should ignore, but it should not have precedence over the promise of these objects as targets of exploration during the next millennium.
Perhaps one reason to explore and further understand comets stems from their probable contributions to our own origins. Scientists have calculated that the oceans of the world and most of the other waters on Earth were delivered here by comets.
Planets were being heavily bombarded, and we see the record of that on the lunar surface. Look at the surface of the moon and all those craters. They reflect that shooting gallery that the solar system was 3.8 billion years ago, as comets and asteroids were being scattered around, as the debris from the planetary formation epoch was being swept clear of the solar system. That period was when the flux of comets would have been the most intense, when any cometary contribution to the Earth was at its peak.
Tens of thousands of large comets impacted the Earth in its early history, depositing a huge amount of water that created our oceans. Recent studies of Halley's and other comets conclusively tie certain isotopes of hydrogen found in most comets with those found in the oceans, a sort of chemical fingerprint. So the next time someone drinks a glass of water, they're essentially drinking part of an ancient comet that impacted with the Earth billions of years ago. Exciting recent discoveries of organic compounds in comets further suggest that they may also be responsible for bringing the spark of life to Earth, and provide yet another compelling reason to study these cosmic travelers. For example, water vapor was found on Halley's Comet, which led to the search for organic molecules in other comets. As a result of various studies in the comets Halley, Hyakutake, and Hale-Bopp, a variety of organic molecules have been discovered, such as methyl alcohol and methane, among others.
One of the main constituents of comets is the organic solid material in them. Now, organic molecules are molecules that contain hydrogen and carbon, often in combination with other things, but lots of hydrogen and lots of carbon. And these are the molecules that are especially interesting in the context of the origin of life on our planet and possibly elsewhere in the solar system or elsewhere in the galaxy as well.
One of the mysteries of the Earth, as we've explored its geological record, is how soon life appears. Earth forms 4.5 billion years ago. The tail off of the formation of the Earth is about 3.8. And right away, we see evidence for life. There's definite evidence for life at 3.5 billion years ago, and there's good suggestive evidence in the carbon isotope record for life at 3.8. So it's looking like the Earth is forming and life is appearing very rapidly, instantly, geologically speaking.
So when we see these organic compounds in cometary nuclei, the methyl alcohol, formaldehyde, ethane, methane, we know that some of these were delivered directly to the Earth by the impact of comets. And this tells us that we didn't need lightning storms and complex processing of a methane ammonia atmosphere on the Earth in order to make these complex carbon, oxygen, nitrogen compounds, which are the precursors to biology, to life. They were actually delivered here by the impact of comets.
We can imagine that on comets, there might be the precursors to important biological molecules. For example, there might be hydrogen cyanide and formaldehyde, and these very simple organic molecules. When those molecules were brought to the Earth, they were mixed in the liquid water broth where they reacted to form sugars and amino acids and other things. So we can imagine that the raw ingredients were in the comets, but the soup, the primordial soup, was made on Earth in the liquid water. So that's one way in which comets could have brought the basic building blocks of life to Earth.
If our oceans were deposited here by comet impacts, then the other planets of our inner solar system should also have received their quota of comet impacts as well. It is not difficult to see how life could evolve on other planets, such as Mars. Early life on Mars could easily have evolved along the same lines as Earth.
Mars, we're confident, once had a lot of water, because we see the geological evidence for flowing water, possibly for glaciers and other things that were created by moving water in a liquid form. But we know that it doesn't have any liquid water now, so we think that it has all evaporated or has seeped into the ground and is frozen as permafrost. Venus, on the other hand, must have received water from comets as well, but we are fairly confident that it's been so hot on Venus for all of its existence that the water had readily boiled away and is simply not stable because Venus is so hot.
There are some scientists who even believe that life forms themselves could be transferred from one planet to another by such impacts.
So people have begun to rethink of the notion that maybe life is more widespread than we realize, and that maybe, imagine a planet somewhere far away. There's life on that planet. And the impact slams into the surface of that planet, knocks a piece of rock up and out. That rock is carrying organisms from that planet. They get carried into space. By one process or another, they're ejected from the solar system of origin and carried through interstellar space, ultimately to come slamming through our own solar system and landing on Earth. And that's a direct way to transfer life from one solar system to another.
It has been suggested that fossilized life forms embedded in rocks from Mars were delivered to the Earth in the same exact manner, raising the possibility that living organisms may similarly be transferred. Everything that we've learned about comets and asteroids provides a better understanding of ourselves and our place in the universe. Comets and asteroids may also represent stepping stones to the solar system as potential resources that could be exploited for space travel.
The most valuable thing is the thing we most often take for granted, the air we breathe and the water we drink. This is what comets have in abundance. And I believe that to spacefaring race, those having a ready source of those things that can support life, that have minerals and metals and the life-supporting materials available in easily extractable form, that is in fact the true value of these things for space exploration in the near future.
For these reasons, several countries are stepping up their studies of comets and asteroids by sending out probes and satellites. Future plans include unmanned sample return missions and even human exploration missions. The first of these studies is NASA's mission NEAR, which launched in early 1996 for a near-Earth asteroid rendezvous. This mission will attempt a close encounter with a 20-kilometer wide asteroid. NASA hopes to send the probe to within 350 kilometers of this potato-shaped object known as Matilda. Perhaps the most exciting mission to an asteroid has been proposed by Japan. This plan would include sending a spacecraft to actually land on an asteroid and bring back a small sample for analysis.
We have a series of missions to the solar system. We shall have a mission to the asteroid Nereus. The launch is planned for the early 2002.
It will take a number of years for the probe to approach the asteroid, then orbit it briefly to scan its surface, and then finally to land on it.
In the case of the asteroid, we are targeting toward a very, very small object, and we have to be very careful to tap its surface and pick up some samples. And escape is not difficult because its gravity is very small. From the asteroid, we can observe the composition of the very primordial substances in the solar system.
This mission is a necessary first step toward a human exploration mission and potential exploitation of such asteroids for their minerals.
We like to study all the entities in the solar system. So we tend to take this mission as a first step toward our expanding exploration into the solar system. And as a Japanese space activities as a whole, there are studies toward the future manned flight, but at this moment there are no concrete plans as yet.
Another sample return mission, called Stardust, has already been approved by NASA for a rendezvous with a comet known as Wild 2. It is currently slated for launch in 1999 and will intercept the comet in 2004.
We send our Stardust spacecraft flying past the comet. We don't land on the comet. We just fly past it as slowly as we can, by 6 kilometers per second. And we expose this magic material called silica aerogel, which is like a low-density glass material. And the particles surrounding the comet impact themselves into this aerogel during the flyby. And that's what we bring back.
This array will catch the comet's particles much like a fly swatter. Microscopic-sized dust particles penetrate one side of the aerogel, becoming embedded and protected, while leaving a fluorescent track.
It's pretty much like a police forensic lab taking a gun and shooting a bullet into a box full of cotton in order to grab the bullet. That's basically what we're doing, except we're doing it at a much higher speed. 6 kilometers per second is a very low speed for a flyby of a spacecraft. but it's much faster than the fastest spinning bullets. And so it is a technological challenge to do this.
After intercepting with a comet, the Stardust probe will transport the material back to Earth in 2006. The probe will detach a pod carrying the cometary material, landing in the Utah desert. Since the materials comprising comets are believed to be the least changed since the very beginnings of the solar system, these particles will be analyzed for clues to planet formation and early evolution of our solar system. The European Space Agency, or ESA, also has plans for sending a space probe to a comet for a long-term mission.
They had flown a couple of years ago a very successful mission called Giotto to Comet Halley, and they now just want to, which was a fast flyby. Now ESA is just going out to launch in 2003 spacecraft towards another comet, but for a rendezvous mission, and see how the comet develops, how it evolves and emits gas and dust and things like that.
After these unmanned probes have completed their missions, the next step would be to send a human exploration mission to actually land on a near-Earth asteroid.
A human mission to Mars would be expensive, it would take a long time, and it would be very difficult. A human mission to an Earth-crossing asteroid would take less time, it would be less expensive, and it would be less difficult in every way. It would be a lot less dangerous. And that's one of the reasons that before we go to Mars, we're going to have to practice on an Earth-crossing asteroid.
Theoretically, with so many diverse resources available on comets and asteroids, it should be easier and cheaper to establish a permanent presence on these bodies than attempting the same on a distant planet like Mars. It may even be possible to establish highly profitable mining colonies on comets and asteroids.
What they're made out of is really very tantalizing. Their compositions can range from solid metallic alloy on one hand, which by the way would almost certainly contain trace amounts of gold and platinum, all the way to the other extreme of extinct cometary nuclei, and we think some 10% of the Earth-crossing asteroids must be extinct cometary nuclei, and although they're going to be dark on the outside, they're going to have interiors made up of water ice.
Now, the feedstock for petrochemicals is hydrocarbons, ethane, methane, and so forth. And so what we can now show is that these comet nuclei contain all of the chemicals needed to sustain life and also to support a rather prosperous petrochemical industry in space. And this means that the dream of pioneers on building space colonies that could be self-sustaining is not so far-fetched after all.
And then there are others that are made of different compositions of rock, including some that have organic compounds, very complex organics, which also would contain maybe chemically bound water, but also could be used to grow food, to develop biomass for growing food. So these are the natural resources of space. No doubt about it, they are the gold mines of the solar system.
If the human species is to truly become a spacefaring nation with colonies on Mars or one of Saturn's moons, then comets and asteroids may eventually become stepping stones to other planets, serving as supermarkets and gas stations for space travelers.
If we could locate one of these in close proximity, to a comet nucleus that was far enough from the sun so that it was not actively sublimating material. It was just an inactive ball of ices of these various kinds. Then that material could actually be, if you like, mined or extracted in a rather simple way and used for the purposes of the humans occupying that colony. And this could make such a colony self-sufficient and relatively independent from Earth.
On a more practical note, scientists are developing ideas to use comets in establishing long-term colonies on Mars. They may possibly help speed the process by which Mars could become more Earth-like, with water oceans and a more dense atmosphere.
Mars is a very dry place, but it's not too cold. It's not such a terrible place for life to thrive, human life even, if there were enough water and if it were just a bit warmer. What about the possibility of causing a comet or two or three to collide with Mars, give it an atmosphere, give it a hydrosphere, an ocean, and thereby make it a habitable place?
So we've been looking at the possibility that one could move a comet from the outer solar system and gently, slowly move it in to the surface of Mars, break it up, and let the pieces enter into the Mars atmosphere, where they, of course, would warm up and melt. And that would be a short-lived but very important rain on the surface of Mars. And a few of those could bring Mars an ocean again and provide it an atmosphere and make it an Earth-like world.
If we are serious about trying to have our species survive, we may need, in the long term, to look for another place where humans can thrive. And Mars, changed by the generation of a hydrosphere and an atmosphere, may be just the place.
The ultimate paradox here is that while comets and asteroids brought the building blocks of life to Earth, it would take only one impact to undo it all. Is there a doomsday rock out there with our names on it? Scientists are hoping that we don't wait too long to find out.
Something that's very improbable but has a very profound effect if it occurs. Maybe it's something that we ought to know about. My own personal opinion is that this is our neighborhood, and we should know who's in our neighborhood. Just go around and look at the other objects. Even if comets aren't getting ready to slam into the Earth, I think it would be a good idea to just know who's in the neighborhood and where they're heading. Comets are part of the neighborhood.
I think this then requires that we give attention to dedicated searches for these near-Earth bodies. We need to get an international network of telescopes up and looking at the skies, be henny penny, so to speak.
Because there are so few astronomers out searching for these bodies, there's just no way of telling if one is coming or not. Even if all these thousands of comets and asteroids crossing the Earth's orbit were located and cataloged, they may still pose a danger in future years as their orbits cross our paths. What is required is a very well-planned observation program to pick these up.
Every now and then, we have objects that are tens of meters and larger that do strike the Earth and our planet. And again, it's an international concern. These objects could hit anywhere in our world and on our planet Earth. So I think we have to gain our senses to know we have to go forward in dedicating telescopes and personnel to this project of, yes, watching the skies. The sky is indeed falling.
Well, is there any evidence that there's a comet out there that's getting ready to slam into the Earth? It's hard to say. I hope not, personally. The chances are very small. If you think of the Earth in the solar system, it's a little tiny dot in a huge solar system. Just from random placement, one would expect that the chances are very small. But the consequences are very large. And so it's It's a delicate trade.
It's also interesting to realize that we sit here and talk about probabilities, but that really is an expression of our ignorance. It's not a game of chance. There either is or there is not an object a mile or more in diameter that will strike the Earth in the next century, for instance. In military terms, the missiles have already been launched. It's just a matter of looking. So we can talk about probabilities, but it's not really a probabilistic situation. It's deterministic. Either one's coming or one isn't.
What makes humankind unique is our ability to comprehend our situation on this planet, as well as being able to control our destiny.
The recognition of an impact hazard is a real natural hazard and something we should perhaps worry about. It's quite new. It's only in the last few years. So far, the U.S. Congress has commented on it. The Parliament of the European Union has. There have been a number of meetings, but no one has clearly stepped up and taken a leadership role and said we should spend the money and we should carry out the survey. I hope that there will be increasing interest on an international level in doing that, but we aren't quite there yet.
Unlike the dinosaurs, we should not wait until we feel the ground shaking and see that plume of hot rock vapor coming up over the horizon before we do something to prevent or at least prepare for that inevitable impact event. It is vital to the future of the human race that we learn all we can about these cosmic travelers. We must scan the heavens with telescopes and chart their locations. It is imperative that we explore them with unmanned probes and ultimately to send a human exploration mission to land on one of them before one of them lands on us.